Welcome to the class of advanced life insurance mathematics. And so today we're going to talk about multiple decrement models to start with. Then we're going to switch to transitions at exact ages, how to work with multi-state models in discrete time next to the continuous time models that we've been discussing so far. And we're going to end with insurance products and annuity products, which are designed for multiple lives, right? So there you will have not just one policyholder, but you will have multiple policyholders involved. Okay, but first we're going to start with multiple decrement models. So these are just a special type of multi-state models. So that's good news because it means that we can still use the machinery as we've been developing it so far. And what is special about such a multiple decrement model is that you've got a single starting state, and from there your policyholder can make transitions into one out of a list of multiple exit states. Okay, so you've got several exit states with a possible transition from your starting state to any of those exit states. No other transitions are allowed. So in fact, it's a really simple multi-state model. You see it sketched over here. So we start with our policyholder in state 0, the alive state. And then the whole idea is that we've got multiple exit states, which can be considered, and the policyholder can make a move into exactly one of those exit states. So we call that in actuarial science a multiple decrement model. So these are different forces of decrement which are applicable to the policyholder in the alive state. If you look more in general in the statistical literature, such type of models would be called competing risks models, because you've got several risks over here which are competing with each other, and only one of those risks will win and will cause the eventual exit of the policyholder that we are considering. Good. So that's a fairly simple design. And of course, to do some calculations in such a model, we need the transition intensity. So to go from 0 to 1, some from 0 to 2, and so on and so forth. That's a multi-decrement model or a competing risk model. Now, of course, if we want to think here about meaningful probabilities, starting from the expression for the transition intensities, what we're going to do then is we can look we can look at the probability to stay during a period of length, say t years, in state 0, right? So if you look at the TPX00, that's the probability that a policyholder who is X year old, who starts in state 0, will be at age X plus T still in state 0. So this probability here, if you denote it with or without the bar, you've got exactly the same probability, because of course no transitions from state 0 are possible, such that you can get back into state 0. Okay. So this is a sojourn probability, and if we then use the expression that we developed together 2 weeks ago, I guess, we've got the exponential function evaluated in minus the integrated total force of decrement. So what we have here is the sum over all the exit states in your multiple decrement model, and what you're going to sum is the transition intensity to go from 0 to exit state I evaluated at age X plus S. And we're going to let the S run from 0 to T. That's the most important expression, so to say, in our multi-state, in our multiple decrement model. This is the probability to stay in the healthy state, in the alive state. The probability to make a certain exit is listed over here. So here you've got TPX0I. So that's the probability that you start in the alive state at age X. And before reaching age X plus T, you should be in exit state I. So what we have then is you will stay in the 0 state for a certain while. In this case, up to h x plus s. And then given that you reached h x plus s, you're going to make the move from state 0 to state I. And this point s, during which this move is going to happen, can run between 0 and t. So this is also completely in line with the expressions that we derived earlier on. And then, of course, two obvious boundary conditions are the ones that we listed, that are listed here at the bottom of the sheet. All right, so I hope you recognize these expressions, because this is nothing new. This is something we already discussed before. So we've got an example here to practice a little bit with this setting. So let's do that together. We start with a 10-year term insurance policy that is issued to a life age 50. We've got a sum insured that is payable immediately on death. That's 200,000 euro. We've got premiums which are payable continuously at a constant rate throughout the term. There's no benefit if the policyholder lapses, and we need to calculate the annual premium rate. And some specifications are given here. Now, what is important for us is that in the first part of the exercise, I'm going to do my calculation when there is no allowance for lapses. So that means if there is no allowance for lapses, that the only states that I would have to consider to take into account in my multi-state model is the alive state and the dead state, right? And then I would have to do my calculations in this setting. If I go to the second half of my exercise, then I will see that there is a certain transition intensity for lapses given. And in this case, it's equal to constant 5%. So here I need to design my model in such a way that I can take both the transitions from alive to dead into account, as well as the transitions from alive to the lapsed state. And of course, the whole idea of the exercise is to see what the impact is of allowing for such lapses. So I suggest we do this together as a warming up exercise. I would like to start with sketching the multi-state model that we wish to consider. So that is alive, state 0, and then there is the dead state, which is state 1. And these are the only transitions that I'm willing to assume. So what I got here is I need to write down an actuarial equivalence between the EPV of the premiums and the EPV of the insurance benefits. So what I get here is that the premium rate P, we're working in continuous time, multiplied with the EPV of an annuity that is active or that is paying, as long as I'm in the 0 state, which is issued to a life age 50 and which has a duration of 10 years. Yeah, so this is the EPV of my premiums. If I'm taking into account that I pay the premiums continuously while I'm in the alive state. And I start with a policyholder age 50, and it's a 10-year term insurance contract. So that's what I need. Then on the other hand, I've got the EPV of the insurance benefit. So that's a dead benefit of 200,000. And I'm going to pay this benefit at the moment of making the transition from the alive state to the dead state. Yeah, so that's what I'm doing over here. That's the notation we encountered last week. So I got a capital A to denote the EPV of an insurance product. I denote it with a bar because the product pays at the moment of the transition, so it's in continuous time. The transition that matters to me is the transition from 0 to 1. I issue this product to a 50-year-old, and the duration of the term insurance contract is 10 years. So putting that all together, I've got here the EPV of my benefits. Right. So then the only thing that matters is what can I do about this A bar 50, 10, 0, 0. And we learned that last week. So if we want to value such an annuity product, then we've got the discount factor, e to the power minus delta times t. remember, again, I'm working in continuous time. And then I need to take the probability into account that at time t, there will be a payment, in this case, a premium payment. And the probability that that will be the case is the probability that at time t, my policyholder will still be in the alive state. So I have to work with this guy. And of course, I can wonder, what is this survival probability? So what is my TP50 00? Well, in this case, that's the exponential function evaluated in minus the integrated force of mortality. And the force of mortality here is to go from 0 to 1. And that was given in the exercise, so you can work out this integral and find the survival probability over here. So do note that I only need to take one transition intensity into account here, because I'm working in this particular multi-decrement model where I've got only one exit state, so only one force of decrement that is applicable. And then on the other hand, I've got my A bar 50, 10, 0, 1. And if I would value this product, I would again have the discount factor. I would multiply with a survival probability and then force a transition intensity to make the transition from 0 to 1 at h dt, right? So again, I can plug in what I know from the given in the exercise and find the solution for the EPV of this insurance benefit. So that's the idea. That's my starting point. So if I quickly show you the outcomes of this exercise. So ignoring the lapses, I'm working with the alive death model. You recognize the expressions that I put on the iPad. I can do the calculations and I find a premium here equal to 875.5, let's say. That would be my annual premium rate. If that's okay, then we can switch to the next part of the exercise. So now we're asked to take the possibility of lapsing the contract into account, right? So when we're asked to take the lapses into account, we're going to work with a slightly different multi-state model. So allowing for lapses means that I must be careful about the exit states that I wish to take into account. So now I'm going to define state 1. You lapse the contract, which means you surrender the contract or you cancel the contract. And then the state 2 is the dead state. So here I've got a transition mu x01, and here I've got a transition mu x02, and both are given in the exercise. So again, to value my annual premium rates, I will start from an actuarial equivalence, and I'm going to look at the same products or the same EPVs, sorry. So nothing is different in that notation. But of course, when I write down this, for instance, this EPV of the annuity, I will now have to take into account that there are multiple. So that's my EPV of my premium payments. And here I now have as the survival probability, the TP5000. Here is my exponential function, of course, integral from 0 to t. And now I need to take the sum of the forces of decrement into account. So that's the difference with the previous solution. So now I have to explicitly take into account that in order to stay in state 0, you have to stand against, or you have to resist both forces of decrement which are applicable to a policyholder in state 0. So I got a sum here of the two intensities. And if I look at the insurance product, sorry, the EPV of the insurance product, that will be similar. So I've got 0 to 10 e to the power minus delta t TP50 0, 0, and then ux plus t 0, 1 dt. And of course, here again, for the survival probability, I will have to work with this particular expression. So that's where the difference is coming in. If you value the product in the alive debt status or in the alive debt model versus valuing this product in the multiple decrement setting where you do allow for lapses. So returning to the shades, let us see what kind of expression we get over here. So here we find a premium of 834.5. So whereas in the previous setting, we had a premium of 875. So we see that if you do take the possibility to lapse your contract into account, that you'll get a lower annual premium rate. So first of all, we see that if you calculate the premium allowing for lapses the way we did it on the sheets, then you get a premium that is lower than when you're not allowing for the lapses. So why is that? Of course, because you take into account this possibility that policyholders will lapse the contract, and so that you do not have to pay for the death benefit of those policyholders who lapse their contract. Now, of course, the impact of that, few extra notes on that. So when the lapses are used to reduce the premium, we would call this a lapse-supported business, and it's considered as being very risky in the sense that, like Jonathan already mentioned, it's really hard to find good transition intensity estimates, for instance, for these lapses. You also have, like Jonathan said, perhaps the adverse selection. So perhaps you're left with the policyholders who anticipate somehow that they've got a higher mortality intensity. So you've got several possibilities or several difficulties there in order to quantify this impact. So that's why it's considered to be a risky approach. And as we already saw in the example, we've got two different models used here, but they are connected. And here we see that working in the alive debt model, we're going to do the calculation to calculate the probability that X would die before reaching age 50 plus T. And we would do it like this. If you look at the alive debt lapse model, then we're going to use here a different combined force of decrement, taking into account the lapsing as well as the transition intensity into the debt state. Yeah? So that's what we discussed in the example, that you've got a different setting over here. So I agree with Jonathan's addition. This is, yeah, it's difficult to quantify the transition intensities for lapsing and for the transition into the debt state. If you would try to distinguish there between different characteristics, so to say, of policyholders, perhaps. Okay, good. So that was the first example to illustrate the use of these multiple decrement models. So the take-home message here is that you need to take into account the total force of decrement if you're working with such a multiple decrement model. And then a difficulty, if you would look at the estimation of the transition intensities, is of course that a few extra notes here, but not too much. So what else can we say here? Interest in a simpler model. So if you would focus on a model where you consider only one of the exit states, say state J or state I, and the same transition intensity into this state, then you can look at what we call the associated single decrement model for decrement J. Yeah, so then you would focus only on this model and do calculations for this specific single decrement setting. So if you would see how that goes. Well, first of all, in the multi-decrement setting, this would be our exit probability to leave because of decrement J. You would be working with a probability TPX0J, where you say, okay, I've got the survival probability or the probability to stay in the alive state as SPX00. So what you're going to do here is you're going to sum all the applicable forces of decrement, and then you're going to multiply with the transition intensity to go from state 0 to exit state J at H x plus S, right? So that would be our survival probability, and we use here in the multi-decrement setting the total force of decrement. If we look at the associated single decrement model, then we would isolate, or we would focus only on this single force of decrement, do the survival calculation with that, and then our exit probability would be considered as such. Yeah, and there are some considerations, some relationships, I think, covered in the book between this single decrement setting and the multiple decrement setting. I'm not going to cover them today, so if you find that interesting, you can read more about that in the book. Extra words about these dependent probabilities. That's the probability of exiting the multi-decrement model because of decrement J. Those depend in their calculation on the values of the different forces of decrements that are into place. If you look at the independent probabilities, denoted here with a star, of exiting because of decrement J, then these are independent of any other transition intensities, because then you focus only on the intensity to go from state 0 into state J. So you can read about that. That's what I wanted to say here. There is one extra thing we should mention here, and that's the concept of a multiple decrement table. So a multiple decrement table is going to summarize our multiple decrement model in a tabular form, just like a life table is doing with the alive death model. And what we're going to do here is we're going to calculate survival and exit probabilities for integer ages and durations. If you want to do some calculations in between two integer ages, then you should use some fractional age assumption like we've been doing in one of the first classes in order to do calculations for non-integer ages. So what I want to say here is, I think it's pretty simple, and we're going to use this in one of the next examples, but we're going to start with a group, for instance, of size 100,000 people. So that's going to be Lx0, the radix of our table, at initial age x0. And then we're going to say, well, the people who are still in state 0 at age x plus t, we call them Lx plus t, and those are, of course, formed by multiplying the size of the initial group with the probability of being in state 0 at age x0 plus t. Yeah. Now that I see this expression here, then of course I should have an x0 here as well, right? So that's a small typo, making the notation not very much consistent. If you look at the number of people who leave the table because of decrement J, what you're then going to do is you're going to denote this with dx, and then with the superscript J to denote the force of decrement, and you can calculate this expected number of people who leave because of cause J as the size of the group where you started with multiplied with the probability, in this case in 1 year, to leave because of decrement J. Yeah? So we can put the table together like this. And the whole idea is, of course, that you will have multiple columns in your table where you will denote the expected number of people who leave at each age because of each of the forces of decrements which are into place. So that's what we're going to see later on in one of the next exercises. So that's all I want to say about these multiple decrement tables at this point, as I will illustrate them in one of the next examples in the next session. All right. So that's what there is to say about multiple decrement models. Just a special case of a multi-state model. One starting state, different exit states. We've got the transition intensities for each of them. Not easy to estimate. And you could use them if you want to really differentiate between different types of exit. So what we're going to do now is to take transitions in our multi-state model at exact ages into account. So what we've been doing so far is that within our multi-state models, our transitions take place in continuous time. Yeah? So that means that the probability of a transition in a time interval of length h would go to 0 if the h goes to 0. And we relied on the following assumption, the probability to make a transition from I to j in an interval of length h. We could write that as follows approximately. So what we want to do now is, what if this assumption is not realistic? So what if you want to take into account certain transitions that take place and can only take place at certain very specific ages? So then we can name as examples of situations where the assumption is not valid. For instance, if you look at a pension plan, where many employees would retire at a specific age, for instance, the age of 65 or 62 or something like that. So what if we have this transition from being in the active state into the retirement state at this very specific age only? How should we account for that in our calculations, which so far only handled the whole thing in continuous time? What if we have many surrenders in life insurance immediately before the premium date? So that could also be a case or an example in which our assumption about continuous time and making transitions in continuous time would not be valid. So what are we going to do after the break? We're going to separate our analysis into periods of continuous transition, where the assumption number 3 that I had on my previous sheet applies. And then we have periods of discrete transition. So we have a transition at a very specific age with a certain probability. So we want to take both into account and do calculations for examples which would allow for both types of transitions. So that's a topic in this section. Again, there's no new theory or whatsoever. We're just going to do one example where we demonstrate how to handle these transitions at exact ages. That's the idea. Again, just another example of the tools that we've been discussing so far. And we're going to walk through this example, 8.13, where we look at the following pension plan example. So we've got an insured who is employed in state 0. He is alive, and then he can make one out of these 3 possible exits. So he can die, he can retire, or he can leave the company and go work elsewhere. Yeah, so we want to use this setting, this multiple decrement model, and we want to take into account that the exits from employment, that these can be modeled with this 3 decrement model in the following way. Yeah. So you've got a specification here of your forces of your transition intensities. So you see, for instance, that to go from 0 to 1, and remember 1 was leaving the company, we can only do that before the age of 60. After the age of 60, we will assume that nobody will leave the company, and so on and so forth. For instance, retirement, that's to go from 0 to state 2. Retirement cannot happen before the age of 60, and then between age 60 and 62, I guess this has to be smaller than or equal to 62, not greater than or equal to. Between age 60 and 62, you've got the following constant force of retirement. Now, besides this, there is also some additional transitions which are possible. So in addition to the continuous time exits from the previous sheet, We will also take into account that at exact age 60, 20% of all the employees still working will retire immediately. And at the exact age of 62, all the remaining employees will retire immediately. So these are two additional transitions at the exact age of 60 or at the exact age of 62, which we need to take into account in our calculations, next to the forces of transition that we had on the previous sheet. Does that make sense? That's what we're going to do. So we're going to try to incorporate these and design, value an insurance product on this multi-state setting. So first of all, I'm not sure if I listed the insurance product. I guess it will come on one of the next sheets. So let's start from here. First of all, we're going to ask what is the probability of survival to an age 59 plus t, let's say, where the t is between 0 and 1. So if you look at the probability of surviving here, it's the probability to stay in state 0. So it means what I'm going to do is I'm going to take the exponential minus the integrated total force of decrement. So the 0.053 that you see over here should be the sum of all the applicable forces of decrement in this scheme. So do note we take a t that cannot go beyond 1 year, because we really want to break it up to start from time interval to time interval. So if we go back to the specification of the forces of decrement, you've got the 5% over here. That's to go from state 0 to state 1, leaving the company. And you've got the 0.3% over here. That's the intensity of dying between age 59 and 60. And the retirement intensity is 0 below age 60, so we don't have to take that one into account. Good. So by integrating this constant, I get my survival probability for a t between 0 and 1. If I look at the probabilities of exit for that particular year, then I've got the integral between 0 and 1, again, of the survival probability times the force of decrement to go from 0 to 1 at age 59 plus t, or here the force of decrement to go from 0 to the dead state at age 59 plus t. I've got a 0 for the probability to leave because of retirement between age 59 and 60, because the force of retirement is 0 in that age interval. Yeah? So these calculations should be clear. So we work from one age to the next, and we're going to do that in this way to make the distinction between what's happening in continuous time versus the transitions that can happen at some specific integer ages. So far so good. What I'm going to do now is I'm going to summarize these probabilities by filling in a first line in a multiple decrement table to make things intuitive and to keep good track of what can happen in this multiple decrement setting. So what I'm doing is I start with 100,000 employees at age 59. And I say, okay, the number of employees that is expected to leave because of decrement 1, withdrawing from the company, is given over here. So how do I get this number? That's the 100,000 multiplied with this 1 year probability to leave because of decrement 1. Okay, so if I do 100,000 multiplied with this probability, I get the expected number of people leaving the company between age 59 and 60. In a similar way, I've got the expected number of people leaving the company because they die between age 59 and 60. No one is expected to leave because of retirement, because I put the force of decrement equal to 0 between age 59 and 60. Now, of course, if we use this line, if I look at how many people do I expect to reach age 60 out of the initial group of 100,000, well, then the expected number of people who reach age 60 is 94,838, right? So of course, how do I get that? That's the 100,000 minus this number minus this number. So why do I do that? Why do I make explicitly this, this distinction in my table? Because now I can easily take into account the transition at the exact age of 60, where 20% of the active employees would immediately retire when they reach age 60. So the DX2 that you see over here, that's then just the 20% of this number of people who are with the company at age 60. Okay, so if I go then to the next line, denoted here with 60 plus, then those are the expected number of people that was my youngest son, but okay. So if I go to the next line, the number of people who reach age 60 plus, and by which I mean that's immediately after exact age 60. That is then this 94,000 something minus the expected number of people who will leave at exact age 60 because of retirement. So by making this distinction, I can rather easily make the difference between what's happening in continuous time, what is driven by my forces of transition, versus the transitions that are happening at a specific exact age. So if we continue here, we're going to look at what's happening between age 60 plus and 61. And again, 60 plus, that means we're beyond age 60. We're right beyond age 60. Yeah. We're going to work again until the next integer age, and we know that we can handle that calculation in continuous time. So it's again a matter of doing my integrals, taking the appropriate forces of decrement, and so on and so forth. So you see here the exit probabilities because of reason 2, retirement, versus reason 3, dying. And if I work that out, so if I start here with the number of people who reach age 60 plus, if I multiply with the 1 year probabilities that I just calculated on the previous sheet, I get the expected number of people who will leave between age 60 plus and 61 because of reason 2 or because of reason 3. I've got a 0 here because apparently the transition between state 0 and 1 was exactly equal to 0 in my example beyond age 60. That's why you get an exact 0 here. Once again, the number of people who reach age 61 can then be deduced, and I can continue with filling up my table. So the next step is to repeat these calculations for age 61. So again, I will look at the 1 year probability of making the transition, do the calculations, taking the appropriate forces of decrement into account, and so on and so forth. So I fill in the next line, and I arrive at age 62, exact age 62. And what I know now is that there is again a transition at an exact age, namely from all the people who are still active with the company at age 62, they will retire immediately at that age. So that's why I've got the DX2 here, which is equal to the number of people who reach the exact age of 62. So that's how I can take these transitions at exact ages into account in this particular multiple decrement setting. And in general, we would say, yeah, you really have to break it up then in continuous time intervals versus things that happen at a certain specific discrete time point or an exact age in these examples. Yeah, so some additional thoughts, and then I'll take your questions. So we're going to use the T minus and the T plus to make a distinction between probabilities before exact age exits and after exact age exits. Yeah. So we've got time point T, and then T minus is right before T, and T plus is right after time point T. And for example, if I would be asked to do the following calculation, so I start with a policyholder age 59. I want to consider the probability that he goes from state 0 to state 2, so that's retirement, state 2. And I want to consider, is that going to happen in 3 years? What's the probability that he's going to retire in 3 years from now? But I denote it with a 3 minus. So that means that I'm not going to take the retirements at exact age 62. I won't take those into account, right? So if I start with a group of 100,000 people at age 59, then I'll see, if I go back to my scheme over here, that I've got this number of people retiring between age 59 and 62 minus, plus this number, plus this number. So that's how I can calculate my requested probability. I do not take the value here in the last line into account, because that would be retirement at exact age 62, and that's not what I was asked to calculate. So that's how you distinguish between the 3 minus and the 3 plus. In this case, it means retire between age 59 and right before age 62. Retirement at exact age 62 is not taken into account in this probability. If that makes sense, what we're going to do now is look at the rest of the example and really value an insurance product by using the probabilities or the numbers that we have in our table. So we're going to start with the EPV of a so-called death in service benefit of 100,000 euro, which is payable immediately on death for an employee age 59. We have an interest rate of 4% per year. We've got, first of all, an exact calculation that is required in continuous time. And then second, we've got the multiple decrement table that we're going to use in combination with a thing called claims acceleration. And with claims acceleration, what we mean is that we're going to do our payments between integer durations at exactly halfway through the year. And then in the rest of the example, we can do the EPV of a lump sum benefit of 100,000 euro paid immediately on retirement for an employee age 59, again using this claims acceleration. So let's do that together on the iPad. I just want to show this, especially for the people who are not in the life insurance mathematics course, because there are few ideas here like this claim acceleration thing and so on, which are good to see once in this course. Okay, so we're going to start with the EPV of a death in service benefits. So we're going to start with an employee who's age 59. So that's what I've got. I've got an employee age 59, and I'm going to look at the death in service benefit. So that means I'm going to look at the transition from 0 to state 3, because that was the dead state. The benefit is 100,000 euro, and I want to value such a product. I want to calculate the EPV of this product. So if I would write this EPV, I'll get the 100,000 euro. And then if I work in continuous time, I would be looking at my A bar, 0.3, because I'm interested in making the transition from the working alive state to the dead state. I've got my employee age 59, and I'm going to look at a 3-year period, and that's because I follow everybody to the age of 62, right? So here is what we're going to start with. So that's my actuarial notation. And if I'm going to work with this, it was a bit too quick, but if I'm going to work with this, I'm going to split this up in time periods of 1 year to be able to take these transitions at exact ages into account carefully. So I start at age 59, so that's T0, and I've got age 60, that's T1, age 61, age 62. Yeah, that's time point 3, that's time point 2, 3, the other way around, right? So what I'm going to do is, if my policyholder would die in the first year, right, then I would pay my death benefit at the moment of death. Okay, so if I want to value this product that is active in the first year, I would be working with a thing that I can denote like this. So that would be my cover in the first year. And that's covering what is happening, or the deaths that can happen between time 0 and time 1. And if I work out this valuation formula, I'll get the integral from 0 to 1 of e to the power minus delta t. And then I've got e to the power, I'm just gonna fill in the numbers, 0.053 t multiplied then with my force of mortality, force of decrement over here. So where do I get these numbers? That's what we've been calculating in the first part of my illustration. So this is my force of mortality between age 59 and 60. And this is what I got if I take the exponential minus the integrated total force of decrement that is applicable here. One comment, just something you have to be aware of. We have an interest rate that is 4%, but that's in discrete time. So if you have a 4% rate, interest rate, then it means that 1 plus 0 times 0.04 is e to the power delta. That's how your capital would grow over 1 unit of time. So if you need to calculate the delta, then you will be dealing with the log or the ln of 1.04. So that's what I would have to use if I would have to plug in this delta over here. Yeah, because I start from a discrete time interest rate and I want to transfer that into a continuous time discount factor. So that's what happens between time point 0 and time point 1. That's what I know. Now I'm going to look at what's going to happen after age 60, right? Between age 60 and age 61. So I know that if I can look over here, that I know what to do, right? I know I should look at a bar, age 60, duration of 1 year, and I should again consider transitions from 0 to 3. But of course, what I'm doing then is I would value this cover. I would value the death events between 60 and 61. I would value them at time 1 or age 60. But that's not what I was supposed to do. I was supposed to value the insurance benefits that I would have to pay in case of death of my policyholder between 60 and 61. I would have to value them at time 0. So I still need to make the switch from this time point here, time 1, age 60, to this guy, to time point 0. So what I have to do here is I will have to multiply in order to go from here to 0. I will have to multiply with e to the power minus delta because I'm discounting over 1 time unit. And I need to take into account what is the probability that somebody age 59 at time 0 will reach the point 60 plus. Yeah? Because in fact, what I'm doing here is I'm going to start from 60 plus and then value the product until age 61. Okay, so if I look at my blue cover about what's happening between age 60 plus and 61, and if I would value this at time 0, then I get the following expression. So with my blue cover valued at time 0, I would get e to the power minus delta, and then I got 1 plus P5900, and then I've got my integral of e to the power minus delta t, and then the numbers are the following. You can check that later. That's by using my force of mortality and my applicable forces of decrement between age 60 plus and 60. Yeah, so that's for the second year. And if I go back, what's happening in this last year of my cover? So then I'm going to look at what is happening here between age 61 and 60. And I can denote that with A bar 03, 61 duration of 1 year. Of course, that would be the value of discovering green at time 2. If I want to value this at time 0, I will have to multiply with e to the power minus 2 times delta t, and then the probability 2p50 5900, right? So if I put that all together, for the green cover, and it's EPV at time 0, I'll get e to the power minus 2 times delta. I get 2p5900, and then I've got the 1 year cover, e to the power minus delta times t, and then the applicable survival probabilities and forces of decrement. Okay, so that's how we can put it all together. And it's really necessary to do it in that way, at least because I've got these transitions at the exact age 60, which I somehow need to take into account. And I can take those into account by working here with the probability of a 59-year-old to reach the point immediately after age 60. And if you reach that point, then this new cover will start, right? Which I can value in continuous time. Okay. I also split it up between 61 and 62 because I've got these definition of the forces of decrement, which are piecewise constant, so they change from time interval to time interval, and also to take that into account, I'm also making the split between the blue and the green cover. All right, questions? If that makes sense, let me continue with the claims acceleration thing. So that would be, let's say, part, yeah, it was not part B, I think. So let's not call it part B, but let's do the claims acceleration example. So what we do now is, I'm going to draw my timeline again. I'm age 59 at time 0, got age 60, 61 and 62. And now I'm saying if death occurs in the first year, and I used, let's do black here. If death occurs in the first year, then the death benefit will be paid half of the year. So at time t equals 0.5. If I look at my blue cover, if that happens in between 60 and 61, then the death benefit will be paid halfway through the year. And for my green cover, if that occurs between 61 and 62, it will be paid again halfway through the year. It's a difficult session today. We've got a lot of visitors. There's too much Lego in the room. Okay, so how can we write that down? So what do we need? We need the probability of dying in this first year. So the probability of dying here, I can get that from my multiple decrement table. So that turns out to be the following quantity, if you look at the multiple decrement table. And of course, the discount factor that you will then use is v to the power 0.5, where the v is equal to 1 plus the interest rate to the power -1. If you look at the blue cover, the probability of dying between age 60 and 61 If you look at the multiple decrement table, that turns out to be equal to 288.2 divided by 100,000. And here I will discount with a factor v to the power 1.5. And in the last cover, I'm going to use a discount factor v to the power 2.5. And then the probability of dying is equal to, if I consider a policyholder starting at age 59, that would be 324.5 divided by 10 to the power 5. Putting that all together, I can then value the same product with the claims acceleration approach, with the discrete time approach. So let me just return to the sheets to show you where we find these probabilities. So if I look at my decrements over here, I'm interested in the death in service. So that means I'm going to look at this 292.2 out of an initial group of size 100,000. That's the expected number of people who would die between age 59 and 60. I've got the 288.2 here, expected number of people out of an initial group of 100,000 who would die between 60 plus and 61, and so on and so forth. So that's where I got my numbers from. So if I put that all together with the claims acceleration approach, I get the following valuation for this particular cover. Questions on this? If that makes sense, we can also do the final part of this exercise. So let me go back. What we now want to do is we want to look at the EPV of a lump sum benefit of 100,000 paid immediately on retirement for an employee age 59. And again, the interest rate is 4% per year, and we're going to use claims acceleration. So that means we're going to work again in discrete time. Yeah. So if we think about that, how would we sketch that lump sum benefit payable on retirement? So if we would be asked to solve that question, I would again start with drawing my timeline. So this is my benefits on retirement. And I'm going to use, again, the claims acceleration strategy. So I know when this benefit would be paid. So I start with policyholder age 59 at T0. Then I've got age 60 at T1, 61, 62. So that's what I want to consider. And now I need to think about when can somebody retire. So I know that in the first year, between 59 and 60, there is no retirement possible because my force of retirement there was put exactly equal to 0. So the retirement is possible, and I'll denote that in red here at exact age 60. So of course, if I have exact age 60 and I need to discount, that would be with a discount factor of V. Then I can retire in between 60 and 61. And if I would retire between age 60 and 61, then the benefit would be paid halfway through the year. Yeah. So here I need to discount with a v to the power of 1.5. And then again, I've got retirement between 61 and 62. That would be paid halfway through the year. So that uses a discount factor v to the power 2.5. And then I've got finally the retirement at exact age 62. So that would require a discount factor of v to the power 3. So by reflecting in this way, I'll see at least what my anchor points would be. So if I look at my solution, I'll get 100,000 euro, that's the benefit, and then multiply it with the probability of retiring at exact age 60. So if you would look that up in the table, you'll get something like this, times V. Yeah, so that's the probability of retirement at exact age 60. And then I've got the probability of retirement between 60 and 61. So that's going to be following probability. That's what I will multiply with v to the power 1.5. So that is between 60 plus and 61. And then I've got a retirement between 61 and 62. And then finally, I've got everybody retiring, or all the remaining employees retiring at age 62, right? So that was at exact age 62. And this refers to the part of retirement between 61 and 62 minus. All right. So taking all of that into account, I can value this benefit on retirement. So if I go back to my sheets, if I look at my multiple decrement table, and here you see these numbers coming back. So the 18,000 something, the 7,200 something, the 6,000, 61,000, divided then by the initial size of my group of 100,000. Those would be the probabilities that an employee would retire between certain ages or at a specific age. Yeah. So here you get this calculation that I explained on the iPad. This accounts for both exact age or exact date retirement with discount factor V and V to the power 3, and then the valuation of your retirement benefits halfway through. So let's move ahead then with the next item that we should discuss. So 2 more things to mention. First of all, we can do something about multi-state models in discrete time. We already touched upon this subject, so we're briefly going to refresh what's happening here, and then we're going to end, if time allows, with some very specific products for joint life products. Yeah. All right, so let's first look into these multi-state models in discrete time. So what are we going to do? So if you go beyond the multiple decrement setting, then it's of course not so straightforward how to work in continuous time. In the multiple decrement setting, we've got these multiple decrement tables, and they allow us to do efficiently some calculations, as we just demonstrated. But what if we want to do this kind of reasoning in the general multi-state setting? Yeah? So how to work with them in discrete time. That's essentially what we want to cover here. If you look at Markov models, and that was one of the first assumptions we made in this chapter on multiple state models, if we work with these Markov models in discrete time, we're going to refer to that as Markov chains. And the crucial assumption to speak about a Markov chain is the following. So given that you have a set of states labeled from 0 to n, if you look at a discrete time stochastic process, written here as yt, where yt refers to the state that you occupy at certain discrete time points, then we're going to say this is a Markov chain if the probability that I will be in a state S at a future time point t plus k, that probability is only depending on the state that I'm currently in. So given the state that I occupy at the present moment t. So I can ignore the states that I've been occupying in over time between 0 and t. Only the present moment. Only the present matters to say something about the future state. Again, an example to illustrate this. I think we can do this on the sheet. So we have an insurer who's using a disability income model to evaluate policies with sickness with death contingent benefits. 0 is the healthy state, state 1 is the sick state, state 2 is death. We have the disability model, so we can go from 0 to 1, from 1 to 0, from 0 to 2, and from 1 to 2. So these are all the transitions that are possible. And what we get here, and this is just a copy-paste from the book, we've got an excerpt from a table with annual probabilities for this 3-state model. And the question is, if you have these probabilities, can you then say something about the transition probabilities over multi-year time intervals? So if we start with an example, so what if we would be asked to calculate the probability that a healthy life age 50 is healthy at age 52? So we would denote that in our notation with 2p5000. So that means you start in state 0 at age 50. What's the probability that in 2 years from now you would be in state 0? So what we're going to do here is we're going to look at the possible paths that my policyholder can take. And you see here that there are 2 paths possible. If I'm looking at calculating this transition probability, that's the path where I stay in state 0. It's going to happen with this probability. So I multiply these 2 one-year probabilities. And I can look at the path where I go from 0 to 1, and then from 1 to 0. That's going to happen with this probability, which is again obtained by multiplying 2 one-year transition probabilities. So if I put that all together, I get the requested probability. So I remember that we've done that last week as well in one of the old exam questions. So that's the whole idea here. You wonder about which trajectories or paths are possible, and you calculate the transition probabilities for every path and add them together. Yeah. You can do something similar for the other probabilities requested here. You can find that in the book. So what if we bring this to a next level, and what if we use this kind of thinking to value an insurance product? Then we continue with the example given here. We've got a healthy life, age 50, who buys a policy with premiums of €1,000, payable annually in advance for up to 5 years. So annually in advance, that means you pay the premium at the beginning of the year. Yeah. The insurer is going to waive the premium for policyholders who are sick at the premium payment date. And we want to calculate what is the reduction in the EPV of the premium income that results from allocating this waiver. Yeah. Compared with a policy where payments are contingent only on the policyholder being alive. So we do 2 calculations without the sickness waiver and with the sickness waiver. So if the sickness waiver is not applicable, then it means whether you are in state 0 or in state 1, you'll have to pay the premium, right? If you look at the product with the sickness waiver, then you're only going to pay the premium if you are in state 0. Yeah. So we need to make that distinction. We pay the premiums at the beginning of the year. So that means that our first premium is going to be at time 0. So we do not have to discount for that. We also have no probability to be taken into account for this first premium payment at time 0. Then the next premium payment is at time 1. So to discount to time 0, we need V. The next premium is at time 2, so we discount with V to the power 2, and so on and so forth. Yeah? So that explains the discount factors, because you pay at the beginning of the year. Then which probabilities do we need to take into account? Well, the probability at time 0 is guaranteed because we start with a policyholder who is alive, yeah, who is healthy. So he has to pay this premium at time 0. So there is no probability, no discount factor to be taken into account for this first premium payment. Neither in the without the sickness waiver or in the product with the sickness waiver, right? Then if you look at what's going to happen at time 1, so in the product without the sickness waiver, you need to pay this premium if you are in state 0 or if you're in state 1. So the probability that you will have to pay this premium is the sum of these two one-year transition probabilities. Same here, and the probability that you will have to pay the premium at time 2 is the sum of these two transition probabilities, and so on and so forth. Yeah? So the difference between my two expressions is that here I should take into account that you also have to pay the premium if you are in the sick state, whereas here at the bottom, I only need to pay the premium if I'm in the alive state, in the alive healthy state, so in the 0 state. Okay, I can do these calculations. How can I do them? Well, I need to find an expression for these guys. At the 2p 50 something. Oh, and I forgot the notation here, so this should be 0, 0. That's a typo. So that should have here a superscript 0, 0, right? So I need to be able to calculate these transition probabilities, and the reasoning that I'm going to use here is a reasoning as follows. So if you need a transition probability over t+1 years, what you can do then is you can ask yourself, well, where will I be after t years? And what's then going to happen when going from time t to time t+1? So for instance, the t+1 p50 0, 0 means either at time t I occupy state 0, and then I will remain in state 0, or I will go from 0 to 0 at age 50 + 1, or at time t I'm in state 1, and then I need to multiply with the 1-year transition probability to go from 1 to 0 at age 50 plus t. So you can use this kind of reasoning to calculate your multi-year transition probabilities in a recursive way. Be careful for the last one, the t+1 p50 0, 2. Well, either you say I'm going to use the same reasoning, and then you'll have to look at what state do I occupy at time t. So either I'm in the 0 state, and then I will go from 0 to 2, or I'm in the 1 state, and I'll go from 1 to 2. Or, of course, the probability that you should also take into account is that at time t, you will already be in the second state, the dead state, and then with probability 1, of course, you stay there at age or between time t and t+1. Yeah, so here there's this extra term to take into account, okay, but what's the probability that at time t I will already be in the dead state. And this is, so to say, multiplied with probability equal to 1. Another reasoning that you can do is you can say, well, the probability here is just a complement of the other two probabilities that I have, because I need to be somewhere at time t+1, and either I'm in state 0, state 1, or in state 2. Yeah. So if you put that all together, you could do calculations like this one. So you could go from the table with the 1-year transition probabilities to this kind of tables with multi-year transition probabilities. And you can plug all of this in your valuation formula for the premiums with and without a sickness waiver. And then you can find eventually the price, so to say, of allocating this waiver construction. Yeah. So that's the first example, pretty manual, of using these discrete time transition probabilities in a multi-state setting, so not necessarily a multi-decrement setting, but here we've got again our disability model, 0, 1, and 2, and doing calculations in this particular kind of setting. What we're going to do is we're going to start with this example, which continues the disability income example that we started with already, but now we're actually going to value annuities and insurance products in this setting. So what we're going to do is, at the end of the 5th year, the policyholder receives a level life annuity if she survives, which is payable annually in advance. There's a benefit of €50,000, payable at the end of the year of death if the policyholder dies before age 55. The premium is €10,000 per year, payable in advance for 5 years, waived on sickness. You are given that, and then a few things that you can use in your calculations. So you've got the interest rate, which is 4% per year. You've got the EPV at age 55 of a life annuity of 1 per year for a life who's healthy at that time. And you've got the EPV at age 55 of an annuity of 1 per year to a life who's sick at that time. Yeah. So there are a couple of ingredients here that we need to distinguish. So we start with a policyholder age 50, and we say that there is a benefit of €50,000 payable at the end of the year of death if the policyholder dies before age 55. That's the first thing. So you work in discrete time, and this death benefit is paid at the end of the year of death. And then if my policyholder survives and reaches age 55, then a level life annuity will start. So a level life annuity, that means an annuity where the income that you receive every year is constant. So that's what this term level refers to. And this annuity is payable annually in advance. So that means you've got a certain benefit every year paid at the beginning of the year. And what is important here is the condition: you get this life annuity if you are alive. So it doesn't matter whether you're in the sickness state or in the alive state, you will get this annuity. So that's important to take into account. And then if we look at, so that's in terms of the benefits here. In terms of the premiums, we have €10,000 per year, payable in advance, 5 years, waived upon sickness, so we know how to take this into account. All right, so let's try to do the calculations. I'm just going to follow the sheet for this. So first of all, if we look at T+1, P5002, that's the probability that a policyholder age 50 will die before age 50 plus T+1, given that she's healthy at age 50, right? So if we want to value this death benefit, we need a probability that our life dies between year T and T+1. So there are 2 ways how we can write down this probability. So either we say we write it down as a difference between the probability of dying before year T and the probability of dying before year T+1. So if you take the difference between these 2 probabilities, it means you capture the probability that your life will die between age 50 plus T and 50 plus T+1. Yeah. Another way to write it is by looking at the possible paths that my policyholder can follow. So here you say, I'm going to see at age 50 plus T where I am, either in state 0 or in state 1. And then I'll need to make the transition into the death state between age 50 plus T and 50 plus T+1, right? So these are 2 different ways to write the probability that we need to have. And we need this probability to value the death benefit. And the death benefit that is applicable during the first 5 years of the product that I'm considering. So if I put that all together, I'll get something like this. So my EPV, expected present value of my death benefit, is given like this. So what is important here, and what students sometimes forget, of course, this death benefit will be paid at the end of the year of death, right? So if death occurs in the first year, you will pay the death benefit at time 1. So you need to discount it from time 1 to time 0 with this factor v. And the probability that that's going to happen, death in the first year, that would be P5002. If I then look at death between time 1 and time 2, that's going to happen with this probability, the difference in, between these two probabilities. And I need to discount with a factor v to the power 2 because I'm going to pay the death benefit at time 2 then, and I need to discount to time 0. And I'm going to do that up to what's going to happen between time 4 and 5. So if I put all of this together, this will be my EPV for my death benefit cover, which is a term contract. It's in discrete time, and I'm going to pay the death benefit at the end of the year of death. Okay, that's okay. If we then continue, so what happens with our life annuities? So with a life annuity, we've got a life annuity of X per year, which is payable from age 55 on, right? But we issue this product to a policyholder who is at time 0, 50 years old. Yeah, so we have this period of deferment. It's a deferred life annuity, and the life annuity is deferred over a period of 5 years. Yeah. So that's why you got here the probability, v to the power 5, and multiplied then with the probability that in 5 years from now, our policyholder, age 50, will be in state 0. So this is the probability that in 5 years from now, I will be in state 0, and my life annuity will then kick in, right? 55 then, and this life annuity will pay me an income of X per year at the beginning of the year, whether I'm in the 0 state or in the sickness state, in the 1 state. And so what is very important here is that you sum these two annuities, or the present values of these annuities, together. Because if you are in the 0 state at age 55, your life annuity will kick in, will start paying, but it will pay you whether you are in the alive state, in the 0 state, or whether you are in the sickness state, in the 1 state. So you need to take these two guys together. And then this, what's happening here, that is to make the discount or the actuarial discounting from age 55, time 5 to time 0. And then, of course, if at age 55 you would be in the sickness state, the life annuity will also start to pay, right? And then we need to look at the sum of these two products. The life annuity issued to a policyholder age 55, who is at age 55 in state 1, and we look at the annuity that's going to pay me an income of, say, 1 per year, beginning of the year, whether I'm in state 1 or in state 0. So again, I need to sum these two guys together. That's the way how I should value the life annuity of X per year, beginning of the year here. How I should value this thing. And then what was given in the exercise is the sum of these guys and the sum of these guys, and those numbers were given. So I can then do the actual calculations over here. There was also this thing about the premiums. So premiums are paid in the first 5 years. They are waived upon sickness. So what you will see is that I got here at this the present value of my premiums, and the size of my premium was 10,000 euro per year, payable in advance for 5 years. So you see that I value that number, or that stream of premiums. I value them with this number. So where do I get this number from? Well, that's the calculation that we did over here in the whole thing, where I assumed that the premium was 1,000 per year. So if I do that times 10, I get the premiums 10,000 per year and waived upon sickness. So with the waiver, I get this number, which I should multiply with 10 to see what my EPV of my premiums would be in this exercise. So putting it all together, I can then solve for the unknown X and find this quantity, the size of my annuity benefit. Yeah. So there are a few things in here. So take a moment to look at this example, in particularly incorporating these two types of annuities here. That's important because the annuity income is paid whether you are in the healthy state, the zero state, or whether you are in the sickness state. Questions on this? If this works, there's just a last comment to be addressed here, and that is how we calculate these multi-year transition probabilities in the discrete time setting. So you may recognize here some famous recursions. Let's say these are the Chapman-Kolmogorov equations, which we already apply in a quite intuitive way to go from one-year probabilities to multi-year transition probabilities in the Markov setting. But let's take a moment to write this in a more general way. Yeah, so that's the whole idea here. I start with a Markov chain with n+1 states. I call the state space S. States are labeled from 0 to n. And then I have the famous relation that if I look at the Pxij over a time period of t plus r years, that I can write them recursively by looking at the t-year probabilities and the r-year probabilities in this particular way. So essentially what I'm doing here is I want to start with somebody who's at hx in state I. I want to know what's the probability that in t plus r years from now you will be in state j. So the way I'm going to calculate these probabilities is by looking what's happening at an intermediate time point, here labeled as t. And so what's the probability that you will then be in state k? And what's then the probability that from k you will go to state j in r years from there, right? And this intermediate state k, that can be any state in my state space. So this system, if you want, that's referred to as the Chapman-Kolmogorov equations, which we can use here to go from one-year transition probabilities to multi-year transition probabilities in our discrete time setting. So to give some reasoning for that, or from some intuition, you will basically say, yeah, if I look at the state that my Markov chain occupies at time t, and I want to know, yeah, what's the probability that, given that I start in state I at time 0, what's the probability that I will be in state j at time t plus r? Well, I can break up this probability, or this event, I should say, by conditioning on the intermediate state that I will occupy at time t, right? So all the possible paths to realize this event are shown over here, and these are all mutually exclusive and exhaustive sub-events. And so these are the only paths that are possible. They are also exclusive. So if I take the sum of the probabilities of all these events, then I get the total probability that I'm interested in. Yeah? So I guess you've seen this at some point, and you can reason about this. All right. So these are Chapman and Kolmogorov. That's what we already intuitively applied to do our calculations over here. What else is there to say? Yeah, we can write this down in a slightly different way, in the sense that we can work with matrices to go from the one-year probabilities to multi-year probabilities. So how do we do that? We put all these one-year probabilities together in a one-year transition matrix, denoted here with Px. So Px is a matrix with dimensions n+1 by n+1, because I've got n+1 states. If I look at the rows in this matrix, then I'll see that the probabilities that I have on one such row should add up to 1, right? Because if I look at Px00, Px01 up to Px0n, well, in 1 year from now, you should be somewhere. So that means the entries in the row here, they're all positive and they sum to 1. So we call it a stochastic matrix. We can work with this px, and we can use the px then to go from 1-year probabilities to 2-year probabilities to 3-year probabilities, and so on and so forth. Yeah. So, for instance, here in our disability income model, we've got 3 states, 0, 1, and 2. You see that if we put the 1-year transition matrix together, that we've got the 2 rows with our 1-year transition probabilities, and then the last row, what we should fill in there is the 1-year probability to go from 2 to 0, to go from 2 to 1, and to go from 2 to 2. Of course, that reduces to 2 zeros and then 1, because if you're in the dead state, you will stay there with probability 1. If I then work out my matrix multiplication between px plus 1, then I'll get the transition probabilities that are applicable to a 2-year time period. Then I'm actually working out my Chapman-Kolmogorov equations. Yeah, so check the last quantity or the last equality, for instance, to convince yourself that that is indeed that the matrix multiplication here indeed corresponds to what my Chapman-Kolmogorov equations would learn me. All right. So to recap this last part, we discussed the use of the Markov model in discrete time. We've got a lot of intuitive reasoning, I would say, over here. We learned how to go from 1-year transition probabilities to multi-year transition probabilities by looking at the paths that are possible. And you can generalize that then to the use of the Chapman-Kolmogorov equations, to the use of the transition matrix, which is here age-dependent. I forgot to stress that, but of course we follow this policyholder in his aging process, so we typically let this transition matrix here be age-dependent. So that concludes, in fact, chapter 8 from the book. So next week I will take some time to do some exercises and to illustrate the calculations in R and so on and so forth. What I want to launch today for the last half an hour is to look into chapter 9 from the Dixon et al. Book, and that refers to, or chapter 9 discusses the design of joint life and last survivor benefits and products. Yeah. So that's what we're going to do. We're going to switch from a product issued to a single policyholder. We're going to switch to a product where you have multiple policyholders. And in the book, we're going to do that with 2 policyholders, but in general, you could do that even for more policyholders if the situation requires this. Yeah, so we're going to consider policies on 2 lives. We'll label them with X and Y, so that's the age of both policyholders at the start of the contract. At the start of the contract, X and Y are alive. They're age X and Y. And they are some kind of partners in some joint life contingent benefit context. So that's the terminology. You've got joint life, contingent benefit. So that means that the payout of benefits is going to be contingent on certain events to happen. So here are, of course, a few examples. So an obvious example is that you have a married couple or a couple who buys an annuity that will pay a certain income while either of them is alive, or an income or an annuity that would start to pay a certain income upon the first death of the partners, something like that. Yeah? So you typically see these constructions being used in pension, retirement kind of calculations. And of course, to practice a little bit your knowledge of the royalties in Europe, my question here to be answered in the chat is, who do I picture here as an example of the couple for which my joint life product would be issued? Very good, Bruno. So Willem, Alexander, and Maxima. It's in fact, I use this example every year, but now it's quite up to date, let's say, topical, because the Netherlands celebrated their Liberation Day yesterday and the day before, and King Willem Alexander gave a very impressive speech on the occasion of that celebration. So the example is really topical. So keep in mind the products that we're going to discuss here, they are often used among partners, couples, married couples, and so on. On the other hand, we could also think about other kinds of constructions. And in this case, I'm referring to business partners who buy a policy that would pay a certain benefit upon the first death of the two business partners, with the idea that when this benefit is paid, it can be used by the surviving business partner to continue the business. And the example that I've been using also for years is the following one. So any idea who these men are? And this is a very, I'm not sure if it's if they are known in international context. So I apologize to the international students. They are not Belgian either, but I guess they're only known in the Low Countries. Any ideas? No clue, Arthur says. Yeah, it's been a while since this example was in the news, let's say. But the guy here is the director, the Dutch director, Theo van Gogh. And this is his business partner, Gijs van de Westerlaken. So they had an art or a film company together. And the reason why I put on this example is because Theo van Gogh died, but he was murdered in Amsterdam. And the illustration here is in fact, it's an example of the kind of products that we're interested in at this point in the course, because they really had this kind of business partner insurance product. But at the time of the assassination of Theo van Gogh, which is several years ago, the insurance company refused to pay the benefit because Theo van Gogh died in an act, or his death was considered an act of terrorism, which was at that point excluded from the policy conditions. So that was a bit of a case in the news then, that the insurance company did not want to pay because it said, okay, the cause of death here and the act of terrorism is excluded at that time, it's several years ago, is excluded from our policy conditions. So that's why I include this example. So Theo van Gogh and the assassination of Theo van Gogh in Amsterdam several years ago. Right, let's go back to the maths. So how do we want to work with this? Well, first of all, we can think about the different types of products. We call them joint life contingent benefits. Think about a joint life annuity that would pay a certain annuity income until the first death of the couple. That's what we call a joint life annuity. So it goes on as long as both are alive. At the first death, this annuity would stop paying an income. Another construction that you can think of is the last survivor annuity. That is payable until the second death of X and Y. So here the income or the annuity goes on as long as one of the partners is alive. That's what we call a last survivor annuity. If we look at a reversionary annuity, that is an annuity where the payments start on the death of a specified life. For example, X. If Y is alive at that time, and it will then continue throughout the lifetime of Y. So that's often part of certain retirement plans in the form of a partner pensioen or een wezenpensioen. So this is the kind of construction where your partner would start to receive some replacement pension or some partner pension upon the death of starting from the death of the partner on. Yeah. If you look at the insurance products, we can look at a joint life product that pays a death benefit on the first death of X and Y. We can look at the last survivor insurance product, which would pay a death benefit on the second death of X and Y. Or we could think of a general contingent insurance product that would pay a death benefit contingent on a specific, to be specified event taking place. Yeah? So these are some common or very popular or very relevant products that we want to consider for valuation. And we're going to do this valuation using the ideas of the multi-state model, because that's the reason why we discuss this joint life and last survivor benefits at this point in the course. Okay, so think about these different products and the stream of cash flows that they generate. So if we want to introduce some notation in order to handle these products, well, first of all, we're going to introduce a random variable for the remaining future lifetime of X and Y. We're going to denote this with Tx and Ty. Yeah? So given the Tx and the Ty, we can think about what is the time until the first death. That's, of course, the minimum of Tx and Ty. What is the time until the last death of the couple? That's the maximum of Tx and Ty. And do note the notation that I've got over here, which is going to be very relevant in our actuarial notation for multiple life products. I've got the XY without a bar, and I've got the XY with a bar, right? And we're going to refer to this as a sort of status. So the status XY is active as long as they are both alive. So we call this the joint life status. Yeah, the status is active or applicable as long as both X and Y are alive. Then we've got XY bar. We call that the last survivor status. So that status is active as long as one of the partners is alive. Yeah, and it stops being active at the moment of the second death. All right, so this notation it's really important. If you grasp this, then you'll be able to quickly go through this chapter, I would say. Any questions on this? Does this make sense? So, and this is an important takeaway: the XY with and without the bar as a kind of status that is active, and the definition of this status. Okay. So of course, if we do actuarial valuation of such products, then we need to take the time value of money into account. So we need a discount factor. We know how to do that. And we also need to take the probability into account that a certain event will take place. So we need relevant probabilities for this joint life product. So here on this slide, I will list a few of the possible probabilities that I can be interested in. Yeah. So for instance, I could be interested in the joint life survival probability. So that is the TPXY. So the way how I remember that is I look at the status XY, and I want this status to be active for another T years. So that means I'm wondering what's the probability that both my policyholders will be active in T years from now, or alive in T years from now. Yeah, so that's the probability that the TXY, which is the minimum of Tx and Ty, is going to be above T. Yeah, they both survive another T years. If I look at the TQXY, that's of course the complement then. That means the probability that X and Y are not both alive in T years from now. So that means one of them could die within T years, or they both could die within T years from now. So it's the probability that this joint future lifetime is going to be less than or equal to t. And then, of course, we can also look at a deferred probability. So that's u bar t qxy. So that means they both survive for u years, and then at least one of them dies in the next t years. So that means that the txy, their joint future lifetime, takes a value between u and u plus t. That's what this notation would refer to. I can do multiple other things, so let's work through them. I could look at tqxy, and I could put a 1 on top of the x. So if I put the 1 on top of the x, it means I want x to die first, so x should die before y, and that should happen within t years from now. Yeah, that's another probability I could potentially be interested in. If I continue tqxy with a 2 on top of the x, then it means x should die after y, and that should happen within t years from now. It's another probability. And then a probability referring to the last survivor status is tpxy bar. So think again of this xy bar status. That's the last survivor status, and that should hold for another t years. So it means they should both survive for another, that means at least one of them should be alive in t years from now. So the last survivor status should be active in t years from now. And so on and so forth, right? So you'll see that you can look at a lot of different possible scenarios here. And actuaries have been using, let's say, relevant notation, actuarial notation, to capture some of these scenarios, summarized here on the sheet. Okay, so what to do with this? Of course, we want to value products. Now, we want to look at either annuity products or insurance products, and we want to be able to work with these valuation formulas. So here you see again an illustration of possible products that you could be interested in. This is a non-exhaustive list, but let's look at a few of them. So if I do A bar XY, it means I look at an annuity. It's in continuous time, and it's gonna pay as long as the joint life status is active. Yeah? So this annuity would pay until the first death. So if I think about how to value this annuity, this is something you learned in the basic life insurance mathematics course. So we know that for an annuity in continuous time, we can see the EPV as the expected value of a certain random variable. And in this case, what is random is the duration of this annuity. Yeah? So what I have here is A bar, and then in the duration symbol, I've got this random variable, here the joint future lifetime, which is going to indicate the duration of my cash flow, of my payment stream. Yeah? And this is what I should calculate, or I need to calculate the expected value of this thing, and we're going to clarify that on the next sheets in order to see the EPV of this joint life annuity. On the other hand, if you look at a joint life insurance product, then you can look at A bar XY. So again, it's in continuous time. And this product will pay an income of, or a benefit of €1, let's say, at the moment that your joint life status stops being active, yeah, or ends, right? So that means, what do we have if we look at this EPV? Well, the joint life status is going to hold, it's going to stop at txy, which is a random variable. If I need to pay my €1 at the moment txy from now, then I need to discount this random variable from txy to 0. So I do that with a discount factor v to the power txy. And of course, I need to calculate the expected value of this thing because I've got this random variable txy that is applicable here. Yeah, if I look at last survivor annuities or last survivor insurance, that's then very similar. I'm just interested in a different status. I'm interested here in the last survivor status, whereas in the first two bullets, I was interested in the joint life status. Also for your reversionary annuity and a contingent insurance, you could in principle write down the EPV as an expected value, but things become quite complicated over here. Yeah? So we'll see that typically you're going to value these products by writing them as a combination of other more standard products. And that's how I would approach this, this valuation. And we're going to see examples of that on the next sheet. Does that make sense? Okay, so maybe we can do a few examples over here. It's just charging my iPad. Let me see whether I need a few extra words on this. So if you, like I just said, if you look, for instance, at this reversionary annuity, then in order to write down the expected present value, we often write this product as a combination of other products that we know, that we are aware of. Or the first relation that we're explaining on the sheet is, what if I do this one? So this is it's an annuity, it's in continuous time, and it's paying as long as one of the partners is alive. Yeah? So it's a last survivor product. And then the claim on our sheet is that I can see this as the following combination of products, right? So what I have here is an annuity on a single life, X, an annuity on a single life, Y, and here as the last part, I've got my annuity on the joint life status. So I quickly want to show you or convince you that this equality indeed holds, because let's say that both X and Y are alive. What's going to happen then I've got an income or a cash flow of 1 in continuous time in the product that is issued over here to the last survivor status. Yeah? So if they're both alive, then I'll receive an income at a rate of 1 per year continuously. But if they're both alive, then this product will pay me an income of 1 at the rate of 1 per year. This product will pay me an income of 1 at the rate of 1 per year. And this guy as well, right? So I'll get 2, an income of 2, as long as they're both alive, 2 per year minus 1 per year over here. So in total, I indeed receive 1 per year, as long as they are both alive, right? Now, what happens if X dies first? And Y is alive? Then the product that I'm interested in, my last survivor product, if X dies, then this product will continue to pay an income of continuously 1 per year to the surviving partner Y, right? And if I look at what's happening here, then I'll see that this guy is going to stop paying, right? Because X dies. And what I get here is this will start or continue to pay 1 at a rate of €1 per year continuously to Y, as long as Y survives, right? And of course, this one, because it's a product issued to a joint life, will also stop paying, so this will drop, okay? So this is indeed what I need. I continue to pay at a continuous rate of 1 per year to the surviving partner Y for the rest of this life. Yeah. And then if Y dies, everything stops, of course. And there's a complete stop. And of course, in the alternative scenario where Y would die first and then X is alive and so on, I get exactly the same reasoning, but then it will be this product that continues to pay the income. All right, so that's explaining a bit the analogy that we have over here. If we would do something similar for the joint life, no, sorry, for the last survivor insurance product, then I'll get this relationship. Okay, so if I look at what's going to happen here, this will pay me an income of 1 at the moment of the second death, so the moment of the last survivor's death, right? So let's assume that, for instance, X dies first, okay, and Y is then alive, so Y goes on. So what's happening here is that if X dies, then this guy is going to pay me 1 at the moment of death of X. But this guy will also pay me 1 at the moment of X death, because this product will pay a benefit of €1 at the moment of the first death. So these two cancel out, and I'm left with this product, which will pay an income of 1 at the moment of Y's death. So that's exactly what this thing then will do. Because in this particular situation, which I stipulate here, X dies first and Y will then be the second death of the couple. If that goes the other way around, so if Y dies first and then X is alive, I get exactly the same kind of reason. Yeah, so this is the analogy between the two products here. Let's look at the last one on the sheet. That's in terms of this reversionary annuity. So here we've got the following product. So that's my reversionary annuity. So what I want to have here is that for this reversionary annuity, you should always check it, their payment should start on death of a specified life. So in this case, payment starts on the death of X if Y is alive at that time. Yeah. So that's what the left-hand side is going to take care of. And then my claim is that that is equal to the difference between the EPVs of these two products. So let's see what happens. So if X dies first, and at that moment Y is alive, then this thing will pay me an income of 1 from the beginning, right? And this thing will pay me an income of 1 from the beginning as long as they're both alive. So at the moment that X dies first, this guy is going to stop, yeah, and this guy will pay on for the rest of the remaining lifetime of Y, right? And the fact that I make this difference here also implies that from the beginning on and until the death of X, nothing will be paid because you've got 1 from this product then and 1 from this product, so that cancels out. Yeah. If Y dies first, then this product will pay nothing. Well, if Y dies first, then at the moment of the death of Y, both will stop. Both products here will stop. So I'll get a cash flow of 0 after the death of Y. So that indeed, the two products that I consider here, they indeed give the same cash flow, right? And they're easier to value. So it's easier for me to work with the difference between these two EPVs than it would be to directly work with this EPV. So that's a point I wanted to make. So I hope that helps a bit. You can also, draw timelines where you illustrate the cash flow of the different products and then make the difference or add these cash flows together to see that you then get the cash flow of the product that you're interested in. Right, so in order to work around the valuation that we need here, we'll need a joint model for the future lifetimes of X and Y. So we need that to derive then expressions for the EPVs of the products. And the first assumption that we're going to make is, what if we assume that both lifetimes are independent from each other? So we assume that the future lifetime of an individual is not affected in any way by the other life. And that's our first starting point. Later on, we're going to generalize that as well. But let's assume that here. It's a simple but strong assumption. And the advantage is that we get quite simple formulas then, which we can easily implement to value these products. So that's my independence assumption. My random variables tx and ty, they are independent. And I assume that I've got a survival model for policyholder X, I've got a survival model for policyholder Y, and then with this assumption of independence, I can work with their joint life and their last survivor status. So here is what you get in case of the assumption of independence. So what is the probability that they will both survive another t years? Because they're independent, that reduces to the product of their individual survival probabilities. So that's tpx multiplied with tpy. What if I look at tpxy bar? So here I'm asking, what's the probability that this last survivor status will be valid for another t years? So that means that tx or that means that tx or ty is going to be larger than t. So that's a probability of a or b. So that's the probability of a plus the probability of b minus the probability of a and b, right? So I can write down this survival probability for the last survivor status. Good. If I have those, I can write down valuation formulas for some of the well-known products. So for instance, look at an annuity issued to the joint life status for another n years. Do that in discrete time. So what you recognize here then is the formula that you've also seen with Jan Dane, where it was v to the power k kpx. But now, of course, the kpx is replaced with kpxy. And that's the probability that my joint life status will be valid for another k years. If I do something similar now for the last survivor annuity, then I need to replace my probability here with the probability that the last survivor status will be applicable for another k years. This is a whole life annuity, so there is no restriction here in the duration of the annuity. And if I look at an insurance product, for instance, if I look at AXY, that would be a joint life insurance product. It would pay me, not me, but it would pay a benefit of €1 at the moment that the joint life status ends. Yeah, and it will do that at the end of, sorry, that was once again. So it is an insurance product which would pay a benefit of €1 at the end of the year in which the last survivor status, in which the joint life status would end. It's getting late. So a benefit of €1 at the end of the year in which the joint life status ends. That's what we need. So you've got a discount vector v to the power k plus 1. That's because we pay at the end of the year in which the joint life status ends. The probability that my joint life status ends between time k and k plus 1 is denoted here. So this means they both survive another k years, and then one of them, or at least one of them, dies before reaching age x plus k plus 1 and y plus k plus 1. So how can you write this probability? You can write it as a difference between two probabilities given here, and this is the probability that they both survive another k years, and this is the probability that they both survive another k plus 1 years. So the difference between the two is the probability that at least one of them dies between time k and k plus 1. So in this way, you recognize the valuation formulas as we've been using them so far, but instead of looking at survival probabilities and etc. issued to a single life, you now have these joint life status or the last survivor status being valid. Okay, I think, yeah, maybe we can just wrap the whole thing up because it's not much anymore and I still got 10 minutes to go. So let me just wrap up the whole thing. Then we don't have to, then you've got it all at once. So why do we make the connection with multi-state models? Because you can, in fact, look at these joint life products. You can look at them with a multi-state setting, and you can say, well, in state 0, both partners are alive. In state 1, X is alive, but Y died. State 2, X died, Y is alive. State 3, they both died. Yeah, and these are the possible transitions here. And what we do here in the independent future lifetime setting is we assume that the transition intensity to go from 0 to 2 is the same as the intensity to go from 1 to 3. So it doesn't matter whether your partner is dead or alive. The only thing that matters here is your own age. In this case, I assume that X refers to a man and Y refers to a woman in the couple. Yeah, so this is a different view on this whole joint life setting, by distinguishing these 4 states and then by making certain assumptions about the transition intensities that are applicable between these states. So the model incorporates in this form the following assumption, namely, a different way to frame your independence assumption is that the intensity to go from 0 to 1 and to go from 2 to 2 is identical, depends on Y's age, but not on the age of X or on the survival of X. And then similarly, the transition to go from 0 to 2 and from 1 to 3, representing the death of X, are identical functions of X age. There is no dependence on Y's age or Y's survival. That's another way to frame this independence assumption. Yeah. All right, so you can look at the exercises related to that. We will take some of them next week. Let me just generalize. So what if we do not assume these lifetimes to be independent? Well, then things get quite complicated quickly. Why would we want to leave this assumption of independence? Because of the death of the first partner could adversely affect the mortality of the survivor. Yeah, this is known in the literature as the broken heart syndrome, meaning that if you follow 2 partners, well, right after the first death, there is an adverse impact on the mortality of the survivor. And so the partner then dies or can possibly die because of a broken heart, so to say. I've got a famous example of that on the next sheet. You could also look at the situation where the 2 lives die together. That's a common shock risk. We'll also see how to generalize our multiple state model to incorporate this. And then, of course, an important argument is often that we say that the 2 lives, they share a common lifestyle, so we cannot assume that their lifetimes are independent because they have similar characteristics, similar level of education, similar living attitude and standards and so on. So this is often given as an argument against this assumption of independence. So here is my thing to conclude with today. It's a question for you. So who is he, who is she, and why are they? Johnny Cash and June Cash, June Carter. Carter or Carter? Yeah, I've always forget. June Carter, yes, and why are they here? But why are they here? He died a couple of months after her death, so they are a famous example of this broken heart syndrome that we mentioned on the sheet. Yeah, that's why I included their picture. Okay. So I suggest that you take a look at the remaining sheets. I think I'm going to conclude here with the promise to return to these examples or to this framework next week and to cover a few extra illustrations. either with R or with pen and paper. That will be the topic of next week's session, right? So what did we cover today? The working principles of multiple decrement models, transitions at exact ages, reasoning with multi-state models in discrete time, Chapman-Kolmogorov equations, and then the valuation of some typical joint life or last survivor contracts.